We talked about this last class. If you draw me a surface with a vector function, right, r of uv, you draw me that surface, then the partials, the two partials give me two vectors. And then if you cross them, you get a normal vector. So if we take that, that's a normal vector, and we divide it by what? Its own length, then you've now made it a unit normal vector. You've made it point out of the surface, perpendicular to the surface, but you also have scaled it to make it a length of 1. Okay? So that's what we're going to define here from now on to be n, our normal vector. It's going to be scaled to have a length of 1. Now, if you take this, I won't worry about the special case right now. So this is what I said about closed surfaces a second ago. If you have a closed surface pointing away, if normals point away, it's positive, points inside, it's negative. All right, that's all we need to now define the last real nice integral of the semester, meaning the last idea. From here on out, what we have are just some theorems that help us do these, all right? So this is the last actual integral that we're going to see. We've seen enough, right? We've got a lot of integrals. So this is it. So let's look at what it's called first. It's called the surface integral of f. And that f is a vector field. See, this is what we've been doing today so far is that f was a scalar function, right? Now that f is a vector field. And we want to take the integral of that vector field over s. S is still some surface. And this is defined to be what's called flux. How many of you all heard that before? Flux. Flux capacitor from Back to the Future? Yeah, but it's in physics we use flux. Electro, yeah? No. Y'all heard it in engineering? No? Flux? So we'll talk about what it is, but we'll talk about what it means like physically, but let's look at it first. What is the integral? Here's the notation for it. So how is this different than the notation we just had? Well, this is not a scalar function, right? This is the same, double integral over some surface. Okay, that's not a scalar function anymore. It's now a vector field. Remember, a vector field is basically you have a space, and inside of it, at every point, there's a vector. Vectors everywhere, right? Vectors everywhere. So we have some field in this space, and then we're going to dot that with d capital S vector. Okay, what the hell does this mean? This is the first time we've ever seen this, right? So let me tell you what it means. This means, oh, sorry, that was supposed to be highlighted as well. The d was as well. This ds with the little vector over the capital S, what it is the normal vector that we were talking about, okay, times ds. What was ds? Remember what ds was? That's from the previous. ds was the magnitude of the cross product. So I want you to bring up your formulas here. Bring this up. Look at, where is it? E. Look at E. It's a little easier to see it here, I think. So here's the new notation, right? Double integral over S. The vector field dotted with ds, and I'm like, what the hell is this d capital S right here with the vector? Well, that, by definition, is the normal vector we were just talking about times ds. Well, what's ds? You remember what ds was? Well, here's the normal vector, right? Remember I said to get a normal vector, you're going to cross the two partials, divide by its own length? Okay, that's a normal vector. And then ds, that's what we started with today in last class. ds is magnitude of the partials, right? Crossed. And then dA, yes? And do y'all see these cancel? Yes. If those cancel, then you're left with this right here, which is basically your field dotted with just the cross product of the partials. Remember what happens when you dot two vectors? You get a scalar, right? So this is going to be a scalar function. We'll be integrating over d. D is going to be the domain. That domain may or may not be visible to us. It depends on the picture, where the surface is. But that's the actual computation that we need to do. All right? So let's try and see if we can understand what this integral is. I tried to explain previously, right, that we could look at the previous integrals like if you wanted to find the mass of something, like a surface. You could use the previous integral. What is this integral used for? It's called flux, right? So what the flux is flux? All right, so here's the idea. And let me start with a different picture before I do this, a much simpler idea. This is a classic example. Let's say we had a river, all right? And we got water flowing through here, this river. And that river has some depth to it. So imagine I'm taking like a cross section of this river, right? So that's the depth. You got little fish down there. Yep, you see the river flowing? So at every point in here, you could look at a molecule as being kind of pushed around and it's being moved around, right, by the flow of the river. So at every point there is some vector, isn't there? So let's say for this particular molecule, there's a vector pushing it this way, and you know, the flow of the water is not just everything in the same direction, right? Things are swirling, and so at every point you got these different vectors, but generally speaking, they all are going downstream, right? But some get turned around. So we talked about, remember, curl, right? Where you're like, they're going, but yeah, even though they're going that direction, they're like spinning at the same time, right? And then we had the idea of divergence, which meant that things were kind of tending to move away or come together, right? So you've got this picture of a river with this flow is kind of like a vector field. And what we're doing is we're coming in with a surface. And in this case, the surface, I'm just going to make this cross section be the surface. And what I'd like to do is measure the flow through that surface, the flow of water. So imagine that that surface is almost like a net. So the water is uninhibited. The water can still flow through, okay? But I want to somehow measure how much flow is going through it. And that's what flux is. It's a measurement of that flow. Now the way we actually calculate it is this. Let's just pick one molecule that's now arrived at the surface. Okay, this molecule right here has arrived at that surface. And at that point, there is a vector, right, that's telling you the direction it wants to go, right? Then we have a vector that is normal to the green. So let's say that the vector that is normal, the unit vector that's normal, I'm going to exaggerate it, that's my normal vector. This is my field vector. What I want to do to figure out the flow through here is I want to take the field and I want to project the field onto the normal vector and create this new vector. And that vector right there is basically the component, it's the component of this vector moving in the same direction that's perpendicular to the surface. So it's giving me the flow through that surface. And I want to calculate what that is, right? And there was a formula. We don't want the vector, we want how long it is, and then we want to add them all up. And that you sum them up, and then you get all these vectors coming out here, all these vectors that have been projected onto the normals, and all those added up together gives you flux. This is the same picture, okay? So in this picture, I have some surface, and I have a red vector, which the red vector is the field. The black vector is the normal. I forget which is what. Hold on. The normals are the black vectors. I'm just looking at this little patch right here. So you can't think about river as much here, right? This is just, you got a field, you go on this little patch. Those are all your normal vectors. Here are the field vectors in green. If I project the green ones onto those black ones, I get those red ones. Now let me take those out. Let me get this out of here. So that right there is basically the field projected onto the normals. So it's giving me the flow out. And what I want to do is I want a lot more of them. I don't want just those. I want a bunch of them, right? And I want to have an infinite number of them in there. And so I get the total flow coming out of that patch. Now this could be water flow. It could be electromagnetic field, like a magnetic field, right? This could be, you know, anytime you're dealing with electricity, right, you have magnetic fields. So we want to measure these things, right? Measure how much is flowing through. Flux. Can we move on? That's kind of the geometry behind it a little bit. If you look at it that way, okay, if you look at it this way, you can make sense out of where this comes from, because if we go back to chapter 10, if we were given a vector and we wanted to project it onto another vector, there was a formula for that. And that's where all this comes from. It's just the projection of the field onto some other vector, and then things cancel out, and then eventually you just wind up with this. Now, I don't go into all the detail of it, but you can look it up. I think we just do an example first. How are we doing on time? God, we're going to have to come in on Sunday. If everyone could be here, please, Sunday. What? No? Okay. We're not coming on Sunday, I guess. I told my Cal 2 class that too. They kind of had the same reaction. All right, find the flux of the vector field across the unit sphere. So we have the entire sphere. Imagine on this sphere, at every point on that sphere, you have a vector, right, from the field. And you're going to take all those vectors, all infinitely many of them, and you're going to project them onto all the normal vectors. And then you're going to find the lengths of those projections, and you're going to add them all up. And that will be your flux. That'll be your flow out of the sphere or into the sphere. It might be in. It depends because the field dictates how much is going in and how much is going out. So some will go in, some will go out. All right. Formula E. Okay, look at E. We have a surface, right? Our surface is the unit sphere. We only have one way of drawing a unit sphere with a vector function in here. And we've done it over and over. We're kind of getting tired of it. The unit sphere, let's do S, sorry. S is my unit sphere. So I'm going to draw that using R of UV is cosine U sine V, sine U sine V, cosine V, and U is between 0 and 2 pi. V is between 0 and 1. Okay, we've done that a lot, right? Okay, that's going to draw me the entire unit sphere. So that's my R. Okay, I need to know my field, don't I? I'm looking at this formula E. I'm now going to do this double integral over, I'll write it down, S of F dot ds, right? This is flux. It's asking for the flux. I put the flux formula here, right here. This really means for us, because we're using this formula E, this is the double integral over D. D is this domain right there of, okay, what do they mean here, just capital F, the vector field? What does that mean, really? Capital F by itself. What does that really mean? It's just the original field, right? The original field, but evaluated where? On R, right? On R. So that means I'm going to have, and it's a vector. It's going to be the vector y. What's y for us? Sine u, sine v, comma. Now z, what's z for us? Cosine v. And then what's x for us is cosine u, sine v, sorry. Okay, that is f. This is f right here. Really, if you don't like that notation, it's f of r u v. That's really what it is. And you can see that in the formula. Do you see on the line before it, when I canceled stuff, do you see I have it written that way? Right there. I have it written that way. But when I go to the next line, I just get rid of it. So this is implied that that means this. Okay. Dot that with partial r with respect to u crossed with partial r with respect to v, but not the magnitude. Not the magnitude. Damn, I wish it was, right? Because if it was, it would just be sine v. So we need to refer back to last class. Or do y'all want to go through the work? Refer to last class, go through the work. Last class? Okay. Then I'm going to need your help. What's partial r with respect to u cross partial r with respect to v? I think I worked it out. Hold on. What the hell? Okay, can you tell me what you have? Because I have it right here.
Negative cosine u.
Negative cosine u.
Sine squared v.
Sine squared v.
And then negative sine u.
Sine squared v.
Yeah.
And then negative sine v cosine v. Okay, all right, that's right. So last class, we showed that the cross of those partials is negative cosine u sine squared v, and then negative sine u sine squared v, and then finally negative sine v cosine v. And then all that dA. Now we dot those two vectors. Jeez, really? All right, so equals double integral. I'm going to go ahead and do my limits of integration now. Okay, 0 to 2 pi, 0 to 1. All right, first multiplication when I dot, I go here to here. Let's do the u's first. Negative sine u cosine u. And then sine cubed v. All right. Remember, dot product, we're just going to add all these answers together. So the next multiplication, I do here to here. It'll be a negative again, won't it? Minus sine u cosine. You want me to do cosine v? Cosine v sine squared v. And then last one will be minus again. Cosine u, do my u's first. And then sine squared v, cosine v. Yikes. Let's see, I went ahead and put, so it's v then u, right? dv du. And as you might imagine, that would be a lot of work to clean up and stuff, right? But we could just go to a computer at this point. And I'm not going to type it in, but I have the answer. You ready? It's 0. Sorry, wish I had better news, but it's 0. Okay. The most important thing for us, like on your final, I'm not going to ask you to actually take this all the way necessarily, right? I may just ask you to just set it up. For the final that you have, take them all the way. I mean, do everything you can. Imagine that's the test I gave to a class. They didn't have computers. They just sat there and did it, right? So see how it goes. All right. Yeah? How we doing? Yeah, we have time. All right, so we just calculated the flux. It was 0. That's boring, but that's all right. Now, if you look at your formulas that I handed out, right, the A, B, C, D, E, we just used formula E, didn't we? But what else is on there? E, F, G, and H. Well, those are basically what we did before with A, B, C, and D. All we were saying in A, B, C, and D were, look, let's look at that surface. Is it something where the clock is running in the background, or is it a function of x and y? Is it a function of y and z? Is it a function of x and z, right? That's the same thing, except these are flux integrals now instead of the surface integrals. So let's look at the next example, and then we'll refer to the page. This is me just summarizing those formulas, but let's look at this one. Find the flux of the vector field f of, okay, so f is xy, comma yz, comma zx, across the surface S where s is part of the paraboloid z equals 4 minus x squared minus y squared that lies above the region where x is between 0 and 1, y is between 0 and 1. So I have a picture there to help you see what's going on. Right, we have a paraboloid. There it is. But we're only looking at it on top of this rectangle, right? This rectangle on the ground. So the domain of this thing, oh, there we go. The domain of this thing, if you were to project this surface down, right? The domain down here is between 0, 1, 0, 1. It looks something like that, right? That's like the domain of this thing on the ground. Right? Yeah. So because of that, because our surface S, right, S is Z is some function of x and y, right? Z is some function of x and y. I'm going to use, which one, F? Yeah, F. I'm going to use F here. And notice how the formula changes. It changes pretty drastically, actually. It says here, if I use formula F, it says that it's going to be the double integral over d, where d is that thing on the ground. And then what? Negative p. What the hell are you talking about? I'll say in a second. Negative p times partial g with respect to x minus q times partial g with respect to y plus r dA. Now, what's p, q, and r? That's the x, y, and z components of the field, right? So that's p, that's q, that's r. P, Q, R. Let's wrap our heads around this first. This z, what is our z function? Z is what? It's the 4 minus x squared minus y squared, right? It's the paraboloid. Yes, that's obviously, if z is a function of x and y. What is our domain restrictions? We already have them, right? They're just handed to us. Thank you very much, right? Like they just gave it to us, right? So we know x is between 0 and 1, and y is between 0 and 1. And so I think we're ready to crank this thing out. Let's try it. Let's try it. Any questions? This will be our last one of the day. Okay, double integral. I'm going to go ahead and put my limits of integration, 0 to 1, 0 to 1. Order doesn't matter. In fact, they're exactly the same, so I can't possibly screw it up. All right, and then negative p. All right, so let's be careful here. Negative p means negative. Now p is what? X times y. All right, that is fine. Negative xy, that's fine. Because remember, z is a function of what? X and y. So our integral should just have x's and y's in it. It should not have any z's. Anytime we ever see a z in here, we have to replace it with this. Okay, so that's p, right? Times partial g with respect to x. What is the partial of g? Here it is with respect to x. Negative 2x. Okay, that's the first part. Minus q. Okay, what's q for us? yz. So I'm going to put y. Now z. What's z? 4 minus x squared minus y squared. Yeah, I know. It sucks. But, okay, there's q. Then partial of g with respect to y. Negative 2y? Okay. So we have negative p times partial g with respect to x minus q with that z replaced times partial g with respect to y plus r. R for us is what? Zx. And z was 4 minus x squared minus y squared x. And then all of this d, does this matter? No. Yx? I'm going to go yx. That's what we normally do. Whatever that is. Right? We can put all that together. Let's see if I worked it out here. Do, 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 do. Yeah, so I cleaned it up. What's that?
I said at least it's not 0.
Yeah, it's not 0. That is true. So you can start cleaning things up, right? You can like put this together. Let's just clean that one up. We won't do any more. If we clean that up, it would be what, like 2x squared y, right? You can do that for each one of these. And then you could do this. Now, again, you would want a computer for this. Like that, the computer can't, at least not yet. Well, probably it can. You find the right computer, right? The right AI chatbot or something can probably set this integral up for us. But I think the human part is still going from here to the integral. And then the integral the computer can do. So the answer here is 713 over 180. I guess I've done it, I did it before, so I have the answer there. That's the flux. That's the measurement of the flow of whatever, through this surface given this vector field. All right, so we're about out of time. Let's just see where we're headed, okay, what we've got next. So the next thing we're going to do after this, well, is it dead? Oh. We're going to do another one of these. But when we do our next flux, it's going to be over this surface. And look at this surface. It's actually 2 surfaces. And then we're going to do another problem. We have to do it over this surface, and this is 3 surfaces. Or 4, actually. Sorry, 4 surfaces. Because you've got the curved part, you've got this front, back, and bottom. So we'll be doing 4 integrals. Okay? And then that will finish up the section on this, right? Then we go to 13.8. Okay? Let's look at this because I want you to know what I'm going to try and achieve the next week. All right? We've got, what, two more examples to do in 13.7? 2 more. And then we come back, and what we do is we talk about something called Stokes' theorem. What Stokes' theorem does is, you remember this integral? I know it's been a while, but do you remember that integral right there? It's work. It's work. It's work along the curve, right? So what Stokes' theorem says, where is it? Here. What Stokes' theorem says is that if you have a curve, right? It's got to be closed. If you have a curve C, okay, and we try and find the work along this curve, this is 3-dimensional, not 2-dimensional. This is 3-dimensional. Stokes' theorem is going to tell us this. If you want to find the work done along that, what you can do instead is you can find the surface integral, okay? And now ignore this for now, but you can somehow turn this work integral into a surface integral over the surface that's bounded by that curve. So you wind up doing a surface integral instead of doing the line integral. And this is a crazy idea because it gives you no restrictions on this surface. In other words, let's say I have a ring. Let's say I have a circle just like this, sitting just like this, xy plane down. If I have that circle and I want to do a work integral along that circle, right? Stokes' theorem says that I can look at, instead of that, I can look at the surface integral over like the disk, right? So I have that circle, then I have that disk. That, whatever that is the answer. But it gives no restriction on this surface S. I could have, instead of done that disk in center, I could make it like a bulb. So imagine I have that circle, but I have this little mound, this surface, like the top of a sphere. I could integrate over that as well. And I get the same answer. It's crazy. Or that could be some Ripley surface, and I can do that. So that's Stokes' theorem. Stokes' theorem is just another way we can do line integrals, and it's going to make some of the problems we did before that were really hard are going to be like laughable. They will be so easy that we'll be like, what? Right? Actually, we'll only do 3 examples. And we did this one in class. I believe we did this one in class. We had to go along a triangle and we did this triangle, and we had to do 3 different curves to do work on each curve. And then we're going to realize, you know what, that triangle makes a surface, and we're going to do Stokes' theorem, and we're going to be like, shit, really? Really? Okay, and we're going to do a couple more. That's 13.8. And then 13.9 is like the grand finale. This is the last section, and it's a super simple, it's just right to the theorem. And what it is it's a way that we can do what? Flux using a triple integral. So you know how I'm going to, next class, I told you I'm going to come in here and I'm going to do those 3 examples. Wait, where is it? Right, I said we still need to do this, right? And we need to do this, and it's going to take us a while to do these. And then when you get to 13.9, we're going to go, hey, guess what? Those things we just did, right? Those shapes we had were solids. We can look at those as solids. And the divergence theorem says, you know what? Instead of doing the flux over that surface and having to do all 4 surfaces, as long as that's a solid shape, we can do a triple integral over that solid and do it using something with divergence, and you get the same answer. And then that problem that we do is going to become simple. So, and that'll be it. That's the end of Cal 3. So that's where we're going, right? We have 2 days to do it. There won't really, I think, be any time for us to sit here and like, let's talk about the final. Okay, let's do some examples. So really you want to look at that final I gave you. You want to make sure you understand it. Work together, right? Help each other out. Come to my office hours if you need help. Okay. Have a good day. We're almost there.